Hello, everyone. Welcome to another Q&A about history of science and technology. So I see a number of questions here. Let's see. There's a question here from Evan. When was complexity science invented? Was there a further back history than digital? Well, I should know something about this because I was deeply involved in the, quotes, invention of complexity science, whatever that means. I would say that the idea that complexity as a phenomenon was something important to study was one that kind of arose in the early 1980s. I was quite central to that whole story, but it had many precursors, as things always do, and it had many things that developed after that time. So maybe we should go to the precursors first. There's the fact that the world's a complicated place is something that was certainly obvious to people from the earliest days of thinking about things like science, by which we mean the Babylonians, the ancient Greeks, and so on. This idea of how does the world come to be the way it is, and is it really as complex as it seems, that's an old story. And so, for example, in ancient Greek times, there was sort of philosophical thinking about could all the complexity of the world somehow be derived from simple underlying elements. Perhaps there were just sort of 5 elements in the world, maybe 5 kinds of atoms, and everything in the world might be constructed from just putting together these 5 kinds of atoms in different ways. That was sort of that kind of story. It was common among the Epicurean school of philosophy, kind of led to people like Lucretius, that's probably 1st century AD, writing, he had this thing, this book effectively on the nature of things, De Rerum Natura, and his version of how might the world be put together was rather lovely, actually. Was kind of the concept that maybe everything is made of atoms, a small number of kinds of atoms, and they are constructed according to some kind of grammatical like rules, much as sentences are constructed out of some particular set of words, which are then constructed out of a certain small set of letters. So, and those words are constructed according to certain grammatical rules. So he imagined the whole structure of the universe might be constructed from rules operating on these small number of kinds of atoms underneath. Well, as science developed, and the next sort of really big push forward in science was in the 1600s, when people started really thinking about applying mathematics to science. I mean, Isaac Newton, 1687, his Principia Mathematica, the full title is Mathematical Principles of Natural Philosophy. Can we apply mathematics to thinking about natural philosophy, how the world works? There had been precursors. People like Descartes had, earlier in the 1600s, Descartes had sort of taken the point of view, I think Descartes imagined that maybe we will be able to understand the operation of something like a tree, much as we understand the operation of a clock. Clocks were very much a thing by then, and it was like, we can see how a clock works. We should be able to, within a limited time, see how a tree works as well. Well, then along came Galileo and then Newton and this kind of mathematical idea. And in a sense, what Newton wanted to do was sort of take the complexity of the world and be able to solve it. And what he did was to kind of identify particular parts of what happens in the world, particularly things in mechanics and in celestial mechanics and astronomy and so on, where you could say, I can just write down a formula. I can use mathematics to just crack this and say what's going to happen. And that was a very successful enterprise. And in a sense, that was the defining beginning of mathematical science, this idea that you could take the complexity of the world, you cut off one little piece of, well, what happens to these, mechanical objects and their motion and so on. That's not talking about how biology works. It's not talking about even how a turbulent fluid works, how clouds are formed, all these kinds of things. It's carving off a particular piece of the story of what happens in nature and being able to say, this is something that we can apply our minds and our mathematics to and kind of crush it and figure out what's going to happen. And that kind of led to this idea that that was what science was going to be able to do. Science was going to be able to take things in the world and just sort of crush them and figure out everything about what was going to happen to them. It's a view of science that is still very prevalent today. It's kind of this idea of, and then we will write down an equation for it and we'll solve it, whether it's about epidemiology or whether it's about physics or any of those kinds of different things. That was kind of a concept and a tradition from the 1600s. And I think then what emerged after that, well, there were a bunch of different kind of traditions and thinking. I know Immanuel Kant, late 1700s, has some quote about it is not plausible that another Newton will arise in the future who can explain the operation of even a single blade of grass, I think he said. So his point of view was there was much in the world that is not going to be explainable, kind of very different from Descartes saying, I think Descartes had said, within 100 years, we will have cracked everything. We will know how everything works, just like we know how a clock works. Later on, Kant is saying there are many things in the world we're never going to be able to do a Newton on and be able to sort of find a way to explain what happens. Well, then in the 1800s, for example, a lot of success in applying mathematics to the physical sciences and so on, efforts to apply mathematics to things like the social sciences, people talking about things like a social physics, that didn't pan out, had a few slightly crazy consequences, but mostly just didn't pan out. But coming into the 20th century, very much kind of a mathematics is making it all work, and a further understanding of mathematics itself, the nature of mathematics, this nature of sort of abstractly created stuff, and how that would and what that would be like, and kind of the idea that we are going to be able to mechanize everything, even mathematics itself. We're going to be able to write down its axioms. This was the concept of David Hilbert at the beginning of the 20th century. We're going to be able to just sort of write down axioms for mathematics and then mechanically grind out kind of all theorems of mathematics. That idea was kind of shattered by Gödel in 1931 with Gödel's theorem, and the result that there's sort of incompleteness from those underlying axioms. There are many theorems that just can't be reached from there. But in any case, I suppose the thing that you could kind of trace the origins of kind of thinking about complexity, there was a sort of a general hope that math is just going to solve it all. And that hope kind of continued, for example, in physics, it continued until pretty close to the present day. In other fields, like biology, for example, it was like, yeah, math, it's going to do something, but it's not that important to biology. There isn't really a theory accessible there. I don't think that's quite true, but that's been the prevailing view. Now, for example, when it came to, I don't know, explaining sort of one of the most obvious examples of sort of complicated stuff in the world is what we see in biology. And the question was, where does that come from? And that was something very confusing. And it was, did God just create all the creatures one day, sort of at a particular moment, or was there some past history to that? And both Erasmus Darwin and then later Charles Darwin kind of was establishing this idea that there would be an origin of species, and this idea that this complexity in biology somehow had some sort of theoretical origin. And for Darwin, that theoretical origin was the idea of natural selection and the idea that species progressively evolved from each other and so on. And Darwin, I think, believed that the complexity that we see in biology was something about which there would be a natural law, somewhat analogous to Newton's law of gravity, for example. I think I say this with some frequency. I mean, the very last sentence of the Origin of Species book of Darwin's essentially said, just as the Earth goes circling around the sun according to the fixed law of gravity, so it is that more and more species, including getting to the higher animals, so to speak, have been and are being evolved, so to speak. So Darwin had this kind of idea that somehow from natural selection, he didn't quite know how it would work, somehow from natural selection, there was sort of an inexorability of the production of complexity in biology. And I think the thing that so that was sort of one branch. There were a few attempts to sort of apply math to biology, particularly Darcy Thompson in the 1917 and then to 1941. His book on growth and form was a kind of an attempt to sort of say, let's use ideas from math and say the form of the such and such organism follows this mathematical curve and things like this. That wasn't this idea of sort of how would math relate, and by math one often meant kind of the ability to sort of just put one's arms completely around the phenomenon and just write a formula and answer it. That whole question of how sort of that encompassing achievement of math could relate to what was seen in the natural world was a recurring question. I mean, I think, who was maybe even Leonardo da Vinci. I think a chap also called Albertus Magnus. This was in the 1400s and so on, and talking about how the book of nature is written in mathematics. I mean, that's a sort of a precursor of the sort of the Galileo Newton development. But I think they had it's maybe what they meant by mathematics is a little different from the kind of the post-Newton math will solve it all. We'll just get a formula for what's going to happen. Okay, so then we're in the 20th century, and there's sort of a question of what the kind of development of thinking about kind of how to explain nature. Physics had carved off the particular things that physics had carved off and was successfully able to mathematicize them. Biology had sort of there were various times when there were attempts to do sort of theoretical biology that happened in the 1930s, 1940s to 1950s. That was the sort of efforts to make theoretical biology had some effect on this kind of on this arc of complexity. But there was a different piece that I don't think was recognized at the time as being very significant, which was the rise of the idea of kind of formal computation. And that sort of came from the notion that just as in ancient Greek times people were asking, were there atoms from which one could make everything in the world, so by the late 1800s, people were kind of asking, is there an abstract raw material from which one can make everything we talk about? And so that was something, for example, Gottlob Frege in the 1870s was saying, well, can we use logic as the foundation for everything? Can we build mathematics, for example, out of logic? He started doing that. He ran into various paradoxes and things. In 1910, Whitehead and Russell came out with their Principia Mathematica, which was a sort of a big, almost show-off adventure in seeing how you could use logic to kind of build mathematics from. And that kind of led to this idea that maybe there was a sort of a formal underpinning to things. Hilbert had also talked about, as I mentioned earlier, could one just sort of set up axioms and then start sort of mechanically grinding out the theorems of mathematics? The idea that there was a formal sort of set of atoms of the world, different, not physical atoms, but a kind of an abstract set of atoms. Could that be logic? Well, what happened, there were a series of developments that sort of led to our idea of computation. One of the earliest ones was a chap called Moses Schoenfinkel in 1920, who invented this idea of combinators, which are kind of these formal mathematical function-like things that can be used to construct what we would now call any computation. Nobody understood it at the time. It's been hard to understand for the last 100 years. I actually wrote a little book about combinators, that sort of started with the centenary of combinators in December of 2020. But combinators were kind of the first full example, very hard to understand, of how you could use kind of the algebraic-like constructs to create what we now think of as computation. Then Gödel in 1931 had his version of this with general recursive functions. Emil Post had a version with essentially string transformations. And then Turing, 1936, Alan Turing came up with the idea of a Turing machine, which is a more sort of mechanically understandable version of the elements out of which you can build something which is like a machine for computing. But still, it was kind of a sideshow. It was something where people said, well, yes, you can make these kind of computational constructs. They are things relevant for thinking about the ways that we think about things. They may or may not be relevant for thinking about the natural world. Even Alan Turing himself, later in his life, in the early 1950s, started thinking about biology and didn't imagine that he should use Turing machines to do that. He went back to kind of the mathematical equations approach to do it. So the idea that things like Turing machines might be relevant to the natural world was something that really didn't exist at that time. Well, as I say, in biology, there were a series of kind of formalization efforts. So, for example, 1943, Warren McCulloch and Walter Pitts come up with their formalization of neural networks, kind of applying logic to these things in biology that were actual nerve cells and so on. That was a sort of piece of formalization that's had its own complicated life they can talk about. Then, John von Neumann in the late 1940s, early 1950s, was sort of trying to formalize biology, trying to imagine, could there be some machine-like system that would, for example, be a self-reproducing organism? He had the idea that, well, biology is very complicated. So if we're going to make something that does something like biology, we have to go to lots of trouble to build that. We have to build this elaborate engineering-like construction with, thousands, tens of thousands of pieces and so on to be able to do the kinds of things like self-reproduction that we see in biology. In the end, it turns out that's not the right intuition, but the intuition at that time was, we want to make something complicated, let's put in lots of engineering effort, because that's our experience of building things ourselves that are going to be complicated. By the way, that had sort of was a reflection of an earlier kind of issue, which was the idea of, well, how does this relate to, was life created by God, so to speak? Did you have to have something supernatural to come in and create something like life? And a very sort of a common quote was, if you find a pocket watch, mechanical pocket watch in those days, lying on the heath somewhere, lying on the street somewhere or something, and you look inside it and you see, it's got all of this complicated machinery and cogs and so on, and that was made by humans. Then you look at a biological organism and you look what's inside there. It's immensely more complicated. So how could it not be the case that whatever made that biological organism was somehow a supernatural thing, a thing with capabilities far beyond the capabilities of us humans? And that was kind of an argument. It was part of the natural theology kind of argument. A person called William Paley had a whole book about, it was about natural theology. And that was part of its sort of argument, a sort of a proof by observing nature of the existence of God. More perhaps sophisticated versions of such an argument about observing nature were more the original kind of the thing with the watch was sometimes quoted as the argument by design. I don't think that's really the right way to say it, because a more significant argument was the very fact that there are laws of physics, the fact that the universe is not an unruly place, the fact that there is consistency in the universe. That was used earlier, I think, by Aquinas and folks like that as an argument for the existence of God. And in a sense, I think it's a more, from what we know now, it's sort of it's a stronger argument to base things on than the argument that, look, the watch looks complicated, but a biological organism looks more complicated, so to speak. But then, so as I say, there was sort of efforts in theoretical biology in the 1930s, 1940s, 1950s, didn't really go terribly far, and certainly didn't kind of have come up with a formalism that started to explain why there would be complexity in biology. Okay, so this takes us probably to the 1970s. What was happening then that was relevant to this? Well, there were, yeah, I'll mention another thing that was relevant. So Alan Turing, in his later years, he died in 1954, I think. But I think in 1952, he was working on biological morphogenesis, how forms get produced in biology. And one of the things he particularly looked at was things like the patterning on things like cows. I think he's the originator of the consider a spherical cow line. But in any case, he was thinking about how you get those dappling patterns, and he came up with the idea of combining chemical reactions with diffusion processes, reaction-diffusion equations. And he observed that, yes, you could probably get sort of complicated patterns through this mixture of reaction and diffusion. That idea got picked up again in the 1960s by people like Hermann Harken and Ilya Prigogine, European kind of chemistry, physics type people who kind of observed that, yes, you could get a certain degree of patterning from this mixture of reaction and diffusion. It didn't really go very far. I mean, more was made out of it than perhaps should have been. It was really a pretty fixed concept. But it led to sort of the general idea that maybe there were sort of patterns that were complicated patterns that you saw in nature that might have some explanation somewhere. And maybe it was a differential equation, which is what reaction equation, diffusion equations are. Maybe that was pretty much as far as it got. Meanwhile, there were efforts to, for example, understand things like fluid turbulence. Again, very much, let's apply differential equations and see what we can say about the solutions to those equations, very much in the Newtonian kind of tradition. One kind of, well, let's see, there were some side pieces to this. One of them was Benoit Mandelbrot. So Benoit Mandelbrot, who I knew, was in the 1970s, well, had originally been involved in all sorts of different applied mathematics, and somehow got involved actually at IBM with language translation and with things like the power law distribution of the fact that the nth most common word in English has frequency about 1 over n, things like that. That's sort of an example of a power law, n to the minus 1 power for that distribution. And he sort of looked at a bunch of different kind of things that followed power laws in sort of physics and in sort of these more social sciences and linguistics and so on. And he was writing a book about this. And I think it was an editor at a publishing company, an American publishing company, who said, this book about power laws and things just isn't very compelling. What about some pictures? And so Benoit worked with a chap called Dick Voss at IBM and started making pictures and started making what became these sort of very iconic fractal nested pictures. The idea of those kinds of nested patterns had originated in people like Sierpinski and Koch in like 1906, 1902, these kinds of dates. Those kinds of nested patterns had originally been thought about in connection with kind of understanding the foundations of calculus and trying to sort of say, well, what's an example, what's a counterexample, and so on, of these different phenomena in talking about when is a function continuous and so on. The idea of kind of nesting like that also is really, if you think about an idealized tree, it has that same kind of nested structure. And that's another thing that kind of was Benoit never really emphasized the tree-like nature of fractals. I think he liked to sort of that wasn't really a thing for him. It was more the final geometry of the pattern. There had been another. There are so many different threads here. Another chap called Aristotle Lindenmayer, who was a Dutch botanist who I met once, who came up with these things he called L system. Well, other people I think eventually called them L systems. These were things where the idea was you would branch. It was a sort of successive branching system like a tree. It was kind of a different fractal-like fractal thing. And those ideas, there were a number of other people who had come up with similar ideas. It was a bit of a sideshow. I mean, it was an interesting thing. I mean, I certainly knew about those things, but it wasn't something that had been sort of widely studied. It was more, well, there were some people in botany and so on who were looking at it, but it wasn't really, and there were a few mathematicians who got interested in it, but didn't really reach the mainstream in that way. So Benoit wrote this book in 1978, I think, called Fractals, that had all these pictures in it and really sort of emphasized the idea of elaborate shapes. And that was sort of one of the precursors of kind of thinking about complexity in its own right. I myself got interested in these things. Well, I had been interested in originally when I was kind of a preteen, I'd gotten interested in things like the second law of thermodynamics and the way in which sort of randomness arises from order in the world. And I had been interested by the 1976, 77 type time frame. I'd gotten interested in a bunch of questions about physics and the universe, about sort of how one manages to get complicated structure in the universe, things like galaxies, things like snowflakes. And so I'd been curious about those things. I didn't really figure much out about them. I was working at the time mostly on particle physics and on cosmology, very much using the traditional paradigm of kind of using mathematical methods and so on, and figuring things out that way. Then for myself, in 1979, I started building my first big computer system, first big computer language, and that kind of gave me the experience of sort of, you just build a computational thing from scratch and get it to do all kinds of interesting things. Then in 1981, I got sort of back to this question of all these things like galaxies, like snowflakes and so on. What was sort of a theory that could sort of start talking about what happens in all these kinds of systems? And I kind of quickly decided that, look, mathematical equations are just not going to make it. And so what was an alternative theoretical foundation that one could use for making models of things? And so I started thinking about using programs as kind of the foundational models for things. And so I started doing computer experiments and very quickly studied these cellular automata. The cellular automata had many names. A chap called Arthur Burks, who had worked with John von Neumann, had given the sort of two-dimensional grid-like versions of these things the name cellular automata. They had other names, tessellation automata, homogeneous structures. Then they had more specialized names when they'd sort of appeared in different areas. Actually, they were related to nonlinear feedback shift registers, but that's not a, they were also sometimes called block maps. But this kind of general idea of you have this array of cells and you have a local rule that tells you, given what the cells near you are like, what will the value of the cell be on the next step? That idea had arisen many, many times. But anyway, I started using that idea. I didn't actually know all of its history when I started using it. but I kind of decided to call what I was doing cellular automata as opposed to one of the many other names that could have been called, and was studying these things and doing computer experiments, and then found this very surprising thing that even when the rules in your program are very simple, the behavior you get is very complicated. That's something I kind of first saw in 1981, and although didn't really appreciate properly until probably 1983, 1984 type timescale. But that was, so for me, that was kind of this idea of from simple rules, you get complicated behavior. That's something which, and that I was very kind of thought that was a very important idea and started kind of trying to encourage other people to work on it, and lots of people got interested in it. At the time, there was a field of theoretical computer science that was called computational complexity theory. The field still exists, but at the time it was very big, and the idea of NP completeness problems that are that have a particular structure and are all sort of equivalent in a certain way, that was a very big thing. And I kind of wanted to avoid calling what I was doing complexity theory, because computational complexity theory was often referred to as complexity theory. So I kind of ended up using the term complex systems research or complex systems theory as kind of the name for this field of investigation, which was how do you go from simple rules to complicated behavior? And could it be the case that when you see complicated behavior in nature, its origin could really be simple rules rather than some very elaborate construction? Well, gosh, there's lots to say about the story of what happened. I mean, I should mention there's many branches. There's a complicated history. Another branch of that whole business was what was chaos theory. And so that was something that kind of originated in the 1800s with the observation that there are phenomena where things get amplified. So for example, you have two balls bouncing back and forth. If they're spherical balls and they hit a little bit off axis, the next time they bounce back, they're going to be even more off axis. And there's going to be a sort of exponential kind of difference between where they hit on successive bounces. And that was a phenomenon that Henri Poincaré noticed also happens in celestial mechanics, that you can have a situation where you have this sort of sensitive dependence on initial conditions, that you can just, if you change just a tiny bit where those balls are going to hit, on the next step, they'll hit in very different places. And in general, if you are sort of bought into the mathematics of real numbers, the mathematics of numbers where you can have any number of digits, what you'll eventually be doing in this kind of is you can excavate those digits. So by the 1930s and 40s, there had originated this field that got called dynamical systems theory. And kind of one of the banner features in dynamical systems theory was a thing called the shift map. And the idea of the shift map is you just take a number, you write it, let's say in base 2, you could write it in base 10 as well. And let's say it's in base 2. At every step, you say twice the number, and you say, but take only the fractional part. Chop off you'd say number goes to twice the number, so you're moving the digits off to the left, but you're chopping the one that's on the left-hand side. And so now what does that do? Well, as you run that map over and over again, you end up sort of excavating all the digits in that real number. Now, the way people think about real numbers, it's kind of like, well, you can pick any real number. There's nothing special about one real number versus another. Like say I make up the real number, 3.141592653, et cetera, et cetera, et cetera. That's just a real number, just like the number 7.6428564 or something. Now, it happens that the number 3.14, et cetera, those are the digits of pi. That's a number which has a story associated with it, but there are an infinite collection of real numbers, most of which have no story at all. But somehow the concept of mathematics and sort of the calculus approach to mathematics is all those real numbers are somehow equally interesting, equally valid. And so when you just say something is described by a real number, you're kind of bringing in any real number. Once you brought in any real number, the overwhelming likelihood is that the digits of that real number will look completely random. So if you apply this something like the shift map, you'll be progressively sort of excavating more and more digits that will seem to you random. So much was made of that, particularly in the 1970s, kind of that turned into this area that was called chaos theory. And kind of one of the big sort of ideas there was that maybe things like fluid turbulence, where you see sort of apparent randomness in flows, would be the result of this kind of excavation of digits. Honestly, it didn't make much sense because in order for one to be sort of seeing the randomness from that excavation of digits, one would have had to put in the initial data to sort of vastly more than the accuracy of the diameter of an atom, so to speak. In other words, you would have quickly run out of data that you could provide. Okay, there was another piece to this story. A chap called Ed Lorenz, who I knew, who was a meteorologist working at MIT, was interested in questions about the predictability of the weather. And he was sort of connected to this dynamical systems theory tradition. And so he said, well, let's take the equations for fluid dynamics and let's make a simple approximation to them, a so-called modal truncation. And he came up with what are now called the Lorentz equations, a set of 3 differential equations. And those differential equations have the feature that they have the sensitive dependence on initial conditions. They have something like the shift map that's part of them. If you change the initial conditions for the Lorentz equations, you'll get sort of a very different result out. The overall pattern, the overall attractor in the Lorentz equations always looks the same, but the details of exactly what numbers will come out will be different. Now, it turns out the Lorentz equations aren't really physically correct. They are just an approximation. I talked to Ed Lorenz at length about this issue. When you don't make that approximation, the thing that happens in real fluids like the atmosphere is that viscosity, the kind of friction of fluids, damps out all of those little details that end up being the sort of excavation of randomness, so to speak. So it doesn't really pan out, but people didn't know that in the late 1970s, early 1980s. And another piece to that whole story was my friend Mitchell Feigenbaum, who this must have been when, 1978 maybe. He was looking at these things called iterative maps, particularly like take the number x and turn it into constant times x times 1 minus x, and just keep doing that over and over again. Sometimes if that constant is small enough in value, x will just go to 0, for example, or x will go to a fixed value. But if that constant is big, turns out with that particular setup, you get this kind of random sequence of values out. It's very much like the shift map. It's excavating whatever the initial value of x that you put in was. If you happen to put in exactly x equals a half, well, you don't get very much out. But if you put in x being some sort of randomly chosen real number, then you'll get sort of the excavation of the digits of that number out. So Mitchell proved in 1978, I think it was 78, realized that there was a certain sort of universality in the way that these different sequences of numbers came out of logistic maps. And that seemed exciting because it seemed to be from this thing where there was so much randomness, there was a piece of regularity that came out. So that was kind of another sort of another thing that was coming into sort of thinking about how complexity would work. In the end, I think chaos theory ended up not being sort of a sideshow to the story. It was made more confusing because a chap called Jim Glick wrote a book called Chaos, actually interviewed me for that book, and somewhat confused things by putting in a bunch of things that I'd told him that were about kind of simple programs to complicated things, and kind of mushed that together with kind of the ideas of iterative maps and so on, and this kind of chaos theory, excavate initial data. And that, I think, that didn't help. It's a well-written book, but it didn't help kind of people's understanding of the distinction between these different kinds of ideas. In any case, I would say sort of an overarching story of kind of the interest in complexity was that many fields had this feature of, we want to know what we can say. We don't just want to say it's complicated, we can't say anything. So in mathematics, for example, there is sort of randomness in the distribution of prime numbers. But that's not what mathematicians wanted to concentrate on. They wanted to concentrate on the regularities of the distribution of primes, things like the prime number theorem, the density of primes has some particular form, things like this. So while there was a fair amount of sort of complexity that showed up, it was mostly, that's not the part we're interested in. In fact, there were lots of cases where people built electronic systems, kind of early digital computers, even programs and so on, where they ran the programs and they saw sort of apparent randomness, apparent noise. And they said, we don't care about that stuff. Like there was early simulation by, well, my friend Marvin Minsky of a neural network. This is from the mid-1950s, where they were trying to sort of get it to do neuron-like things, but there was a bunch of noise that showed up, which I think is the same kind of thing that shows up in simple programs doing complicated things, but that wasn't what they were interested in. What they were interested in was get the neuron to recognize this pattern or whatever else. So it got ignored a lot. And I think the main thing that probably, I guess I probably contributed to this was the realization that there was something that you could get from these simple programs. You got very complicated behavior, and that very phenomenon was interesting in its own right. I mean, at the time, this is early 1980s, I'd gotten a bunch of very good mathematicians interested in this problem. And I think they were trying to sort of crack the problem with math. They were like, these cellular automata and things, that's simple enough. We should be able to just crack this problem with math. They didn't succeed. I think one of the things that I realized, I didn't realize that this is how I'd realized it until many years later, was the very fact that they had not been successful was itself very interesting. And that's what led to this concept of computational irreducibility that I've studied now for more than 40 years. But in any case, I would say that sort of the notion of complex systems research, I'm pretty sure I invented that term, and that was 1984-ish timescale. And what I failed to do, I sort of promoted that idea, like what's now the Santa Fe Institute. I was the one who sort of encouraged them to focus in that direction back in 1984 or so, which ended up happening. But I think one thing that I kind of, and I did things like started a journal called Complex Systems that still exists today, and started an institute for these kinds of things and so on, which doesn't exist today, but because I went on to do other things. But and now we have the new Wolfram Institute, which has a rather different mandate and way of operating that I think is going to work really well, but that's a different story. But in any case, back in mid-1980s, there was this sort of enthusiasm for sort of complex systems research and so on that I think was there were these several pieces, whether it was fractals, whether it was chaos theory, but the one that was sort of the much more, I would say, solid foundation was this kind of idea of simple programs generating complicated behavior. What I failed to do was to really recognize that one should sort of break off the pure basic science of simple programs producing complicated behavior, what I would now call ruleology, from the applications of that, of saying, well, given that we know that rough phenomenon, let's apply it to economics, let's apply it to social science, let's apply it to meteorology, whatever else. And the failure to break that off, as pure mathematics is broken from applied mathematics, I think made the whole enterprise a lot messier. It really wasn't the idea of studying complexity in its own right didn't really happen properly. It all got intermixed with all these kind of applications. I have to say, in 1986, I started working on Mathematica and what's now Wolfram language, and I kind of dropped out of the complex systems business. I had put some effort into kind of raising money to get complex systems to be a thing, but it all went very slowly, and I was impatient and decided I was going to sort of, instead of raising an army to go work on this stuff, I was just going to build tools for myself and work on it myself, which is what I did. And so starting in 1991, I started writing what became the book, A New Kind of Science, which is kind of was a follow-on from my kind of study of how simple programs produce complicated behavior. It was sort of a generalization of that idea. During the 1990s, when I was sort of not, was sort of acting as a hermit and just running a tech company and trying to do basic science, complexity became a bigger thing. I remember I think there was a Time magazine cover about complexity that I kind of thought that's the beginning of the end when that happens. So what actually had happened was that somehow the funding for kind of early ecological climate-ish stuff in the early 1990s, I think, got intertwined with kind of complexity and sort of added some sort of government funding and so on to things that had some kind of complexity angle to them. I'm not sure. I wasn't really involved at the time, and haven't really tracked the history. But it's sort of interesting that there started to pop up complexity institutes, and there are hundreds of them around the world now. But they started to pop up in the 1990s. I kind of came back into the business in 2002 when I finally finished my New Kind of Science book. I think people were sort of surprised to see me back. And I was a little disappointed with what I found in terms of what had happened to the field of, sort of complexity. As I say, I view it as my own mistake for not making more of an effort to break off the kind of pure basic science of complexity from kind of its applications. But anyway, I think in more recent times, well, there's been a fair amount of ruleology done over the years, and I'm hoping to actually really concentrate that a bit in some organizational way in the not too distant future. But in any case, there's been a lot of sort of pure ruleology that's been done, more or less in the tradition that I kind of well, I guess started with studying simple cellular automata and so on in the early 1980s. So it's a bit of a messy history, as I say. It's a history where I feel that some of what was a very, very clean, extremely clean kind of area of very basic science, studying simple rules and what they do, is a very strong kind of thing where the results in that area are very surviving, they're very permanent, they're very formal, they're very abstract, like pure mathematics. And then there's a whole lot of sort of, in the weeds kind of thing with the details of particular fields, which tends to kind of ebb and flow as those fields change and as the emphases of those fields changes. And it's also a certain amount of you're kind of very deep in the weeds, so to speak. And it's not really thinking about complexity at a more abstract level. That was a long answer. Let's see. My gosh. Well, so many questions here. Well, gosh, you guys ask all sorts of interesting questions. All right, let me turn to something. I'm wondering if there's some more along the lines that I was just discussing. Maybe I should. Chatty Mensch says they always forget Aristarchus. And I'm not an expert on Aristarchus. I don't know much about him. So I probably forget him too, and I should do my homework there. Let's see. Well, Taki asks, what role did category theory and type theory play in mathematics? In the early part of the 20th century, well, mathematics became much more abstract in the last couple of decades of the 19th century. You know, David Hilbert was a big part of sort of additional abstraction in mathematics. Just to explain a little bit about the overall arc of development in mathematics, Euclid, for example, when he was coming up with his axioms for geometry, things like that, pretty much thought he was just taking the world as it is and tightening it up a bit so that you could reason about the world as it is. He said, well, I can draw this triangle, but I'm not going to get it quite right. I'm going to have an abstract version of this triangle, but my triangle is really going to be something that is sort of from the world as it is, but I'm tightening it up a bit. And that was kind of the way that mathematics was thought about for a very long time. It's kind of an abstraction of the world as it is. Then in the 1830s, a couple of things happened where people started thinking about mathematical concepts that didn't seem to be from the world, so to speak. So Lobachevsky, for example, had this idea of curved space, where, for example, two parallel lines, which for Euclid just never met, because you draw two parallel lines, they never meet. But for Lobachevsky, he imagined a form of space where those parallel lines could meet or could diverge from each other, and so on. So that was one thing. Then Évariste Galois, also in the 1830s, started saying, well, let's think about, when we think about algebra, x times x is x squared and x minus x is 0 and so on. Let's try and generalize that. He did that for the invention of group theory, where it's kind of like there is a multiplication-like thing, but it doesn't have quite the same rules as ordinary multiplication. George Boole did a similar thing in the 1840s, inventing Boolean algebra, trying to take logic and give it sort of an algebraic form. Then William Rowan Hamilton, I think it was 1847, came up with his idea of quaternions, sort of a generalization of complex numbers, something which were just a construct that you could write down formal rules for and operate with, but it wasn't a construct that necessarily had anything to do with the real world. I mean, Hamilton happened to sort of link quaternions to things like rotations in three-dimensional space, but that was kind of an extra. What he was really trying to do was to do something abstract and formal and generalize complex numbers and so on. So that was kind of the precursor. Now then David Hilbert did something, I think this must have been 1870s maybe. He had a result, mathematical result, and he wanted to prove it. And in his proof, he just said, this must be true, that must be true, that must be true. But when somebody says, show me the thing for which this is true, he couldn't do that. It was a non-constructive proof. It wasn't a proof where you say, you make this thing, I can pick it up and show it to you. It was this thing must exist, and I can prove that with logic, so to speak, but I can't actually pick the thing up and show it to you. And that sort of began for Hilbert this whole idea that you could sort of have mathematics be a disembodied thing that worked from arbitrary axioms and so on. And so these other precursors had kind of led to this idea of mathematics as an abstract construct that just started from anything. Like Hilbert famously said, you could have these axioms be about tables and chairs, as well as points and lines and numbers and so on, and you could operate them just as well. So there was this notion of mathematics becoming quite abstract. And that had also been kind of forced upon mathematics, because in trying to sort of tighten up what calculus really meant and get theorems that really worked and not lots of weird exceptions and so on, there was a need to kind of define these things more precisely. Well, that led to various kinds of developments in early 20th century mathematics, particularly in France. There was kind of a push towards formalism and the idea that just sort of talking about math in concrete terms, actual numbers, actual this was kind of a lower form of thinking. And there was something more abstract, more pure that you could do. And for example, the Bourbaki group was a collection of mathematicians. I guess I knew a couple of them after the time of the work that I'm going to describe. They made themselves a bit anonymous. They named themselves after a Nicholas Bourbaki, who was, I think, an obscure Napoleonic general. And they started putting out these books about pure mathematics. They saw themselves as kind of renegade activists of mathematics or something, who were kind of pushing the more abstract frontier, even in the face of other mathematics that was being done in a more concrete kind of way. But anyway, that led to kind of the construction of some very abstract things, particularly areas like algebraic topology. Meanwhile, there was an American named Saunders Mac-Lane, who I met a couple of times, who sort of got involved with algebraic topology. And one of the issues with algebraic topology is there's a lot of concepts that fit together in complicated ways. And so Saunders Mac-Lane invented this idea of what he called category theory, which was a way of kind of saying how concepts fit together. It had been the case that one had the idea in mathematics of a function. A function would take a number, let's say, and produce another number. Well, there's a sort of a slightly more general idea of a mapping, where you take a set of things, they could be numbers, and you apply this mapping, and you get another set of things. They could be numbers. You can think of a function as being like a mapping from numbers to numbers, let's say. And in category theory, it sort of was, let's generalize this all the way. And it was the notion of objects and morphisms, kind of like things and morphisms are kind of mappings between those things. And then there's the notion of kind of kind of when you have these chains of morphisms mapping this to that to this to that and so on, you have things like functors that are mappings between these chains of morphisms and so on. But it's all very, very abstract. You don't have to say what the morphism is. You just say there are properties of chains of morphisms that are true for any morphism. It doesn't matter what it is. It doesn't matter whether it's talking about geometry or algebra or number theory or whatever else. But that was an invention from, I guess, the 1940s for trying to sort of organize how one talked about algebraic topology. For a long time, it was kind of an obscure sort of, well, you could do that, but I'm not sure why you'd want to. Then in the 1990s, I guess, there started to be more of an application of category theory to computer science. And then kind of category theory became a way of sort of organizing, talking about pure mathematics. At some level, it was a way of importing kind of computational structuring ideas into mathematics. And category theory became sort of a standard language of mathematics by the last 25 years or so. And it's sort of a common thing. But you'll find older top mathematicians who say things like, I'm afraid of category theory. For them, category theory is kind of a bit of a newfangled, a little bit, it's not really stated in computer terms, but it has concepts that are very computational in the way that it sort of abstractly discusses kind of mappings from this to that and so on. Now, a thing that was also part of this question and something that was also a sort of a parallel track in a sense is type theory. Type theory, its origins are kind of messy. Its origins were that Bertrand Russell, when he was trying to do his work with Alfred Whitehead on kind of the formalization of mathematics, was coming up with these things that were sort of strange paradoxes. Is the set of all sets a member of itself and so on? It's these kinds of things about sort of how do you deal with these kind of paradoxical recursive paradoxes and so on. And so he said, well, let's just invent this idea of types where we can distinguish sort of the set of all sets from just a set. We can distinguish these different kinds of things. And that was his way of avoiding these paradoxes. And that was sort of the original origin of type theory, was kind of this way of sort of segmenting things so you could avoid these kind of recursive paradoxes. Now, by the time Gödel was coming along, type theory was still a bit sort of mysterious, and it was sort of part of thinking about infinity in a sense. And there's a lovely quote, footnote in Kurt Gödel's original paper about Gödel's theorem. And the footnotes are often the places where people say the best stuff, because they kind of relax a bit. They're not being as kind of uptight as they are in the main text of what they're writing. But Gödel has a statement there that Gödel's theorem, which tells you things about what you can't say based on axiomatic structures and so on, says, but the human mind might get there, and it might get there by a transfinite series of a sequence of types ramified into the transfinite. So it's a very abstract infinity of infinite hierarchy of types. But that was kind of, type theory was still a little bit of a bit, again, a thing off in the corner as a sort of a piece of abstraction. Type theory, well, types entered computer science in a very pragmatic way. People were making computers, and they had to store data in computers. And they were like, well, we've got these bits that we're storing data, and we're going to arrange this set of bits is going to represent an integer. This set of bits is going to represent the characters in a string. This set of bits is going to represent a real number. In order for our programs not to get confused, we're going to have to talk about the types of data. I actually don't know whether the term type in the computer science sense actually came from Russell's theory of types, or whether it was completely independent use of the English term type to just be the type of data that you're putting there. But in any case, that became sort of commonplace by the certainly by the 1960s in Fortran and things like this, the notion of different types and declaring different types in your programs and so on. So types as practical things in programs were very much a thing. For example, when the C programming language was developed, that was late 1960s, beginning of the 1970s, Dennis Ritchie, who had been a studier of theoretical computer science, he introduced kind of types that weren't just an integer, a real number, a list of integers, something like that. But he introduced types with things like a function that returns a pointer to a function that returns an integer. That was a more sophisticated form of types that was put in a very practical way for computing. So then the kind of as sort of a parallel tracks of category theory is this way of sort of organizing things in pure mathematics that has a very computational flavor. And similarly, type theory can also be thought of as a way of organizing things in mathematics, where you say, you talk about an integer, a function mapping integers to integers and so on. We can think about those things abstractly as types. And that then led to sort of the idea that one could just study types on their own. And that led eventually particularly to homotopy type theory. And particularly, one of the things that is notable is when you have an elaborate enough type, just resolving the question of, is there anything that exists that is of that type, is equivalent to answering a question that you could get by running a program. So if you say the type, we define a type to be things that have, where the square of the thing plus the this plus the that has this property. Those are so-called dependent types. Usually when people have set up kind of type theory systems, they kind of a little bit squiggly on saying, well, we're going to do types that are things that are very sort of statically defined types. When you say, oh, and I want to be able to test out, is it a prime number or something? Is the type a prime? You could say prime is a type. But then when you say, well, it's a prime, but it also has to be equal to 3n plus 1, has the form 3n plus 1 or something, et cetera, et cetera, et cetera. It becomes more of a thing you have to dynamically test if you were implementing it on a computer, for example, rather than a thing where you could say, this is a type. But as you sort of merge those two things together, types become everything. And so they become a way of representing lots of kinds of things. So both category theory and type theory are sort of these ways of abstractly representing things that have a very computational flavor. And the notion of homotopy type theory is, that sort of has a merger with higher category theory. Maybe it's not. Maybe I shouldn't go too deep into this, but uh, uh, the yeah. So that's kind of the story there. I mean, in terms of modern mathematics, there are definitely areas of pure mathematics where category theory is regularly used to organize things. Type theory is sort of regularly used to organize things. There are also areas of mathematics where people don't give a damn about category theory and type theory. There are areas of mathematics where the methods that are used in geometry or whatever else are just methods from those fields, and they don't use this kind of superstructure of category theory and type theory and so on. Um, let's see. Oh my. Des is asking, how would you think about approaching alchemical literature, knowing that these mostly employed coded language rather than being about literal transmutation into gold? I haven't tried to read much alchemy, I don't think. Uh, I mean, alchemy was kind of what turned into chemistry. It was about how do you sort of uh, manipulate substances, with one of the hopes being turn lead into gold, um, and or create the philosopher's stone, which was variously a source of wisdom and an elixir of eternal life, and so on. Um, I think there had been a tradition with people like Agricola figuring out how do you get this piece of rock and that is an ore of a metal like iron and actually get the iron out of it. And that was something that was known, obviously it was known from the Bronze Age and so on. It was in the Iron Age, it was known how you could do things like that. That was sort of organized by, well, oh, I don't know, 500 AD, something like this. And people were systematically writing about that. I think that was a success, so to speak, of a chemistry-like approach. Then there was sort of a lot of, you know, potions, and I think I don't know the relationship between sort of the get good metals out of rocks, which seemed almost magic that you could get metals out of rocks, and that would seem like, well, given that you can get metals out of rocks, why can't you get lead out of gold out of lead? I don't know the connection between sort of that set of thinking and sort of medical potions. Kind of, you imagine the witch's stew or something, the big cauldron, throwing random animal parts and random other things into this cauldron and stirring it up and then telling people to drink it and it's going to be good for them in some way or another. I'm not sure what I think both of those were sort of corners of the alchemical tradition. I'm not sure how they related. In terms of what was written, well, the thing to understand, I mean, ideas are something that there's never really been a good framework for protecting raw ideas in the world. There's people invent frameworks like copyright or something for inventing the way you put a thing on paper or in a computer, and this actual thing with a whole sort of structure and so on to it. But raw ideas have been hard to protect. I mean, ideas that become inventions, they turn into patents and so on. Raw ideas hard to protect. And throughout history, people have had different ways of kind of dealing with that. And I think in the alchemists, their raw ideas, they tended to protect by having them written in code and be secret. I mean, the Freemasons, same kind of story. In modern times, with academia, I think is as scurrilous as it's ever been, with ideas being stolen all the time. I think they're really sometimes people don't write in code anymore much, although they have sort of an analog of that, which is if somebody's gone through a lot of trouble to make data or make a program or something, they tend not to provide that to other people because it's like kind of, well, then they could just do what I'm doing. I mean, I guess I have had a different approach in modern times of sort of doing science in a very open way, where it's just like, you make a picture and something you write, you click it, you get the code, you can run with it. I've kind of gone extreme on the sort of openness side, but that's been I would say it's the anti-alchemical tradition, so to speak. It's kind of the idea of, the only way to preserve your ideas is to keep them secret. I don't really know what. I mean, when you go back and look at archival material, it's the extent to which you can understand it is greatly dependent on the extent to which you really know the material, the content of what's being discussed. So, for example, when you go back and look at, I don't know, what Gottfried Leibniz was writing or what Newton was writing, some of these people, some of what they wrote, it's like, yep, I get it. That maps onto something that I know in today's world. And some of it is like, what the heck were they talking about? I don't understand that. I don't understand that notation, that symbolism, whatever else. Because partly the thing that they were talking about was something that we don't talk about today. It just wasn't a thing that survived as part of the kind of canon of science. And so it's hard. It takes a lot more work to kind of project oneself back into those kinds of things. So in terms of the alchemical literature, I have no idea what, in the thoughts of the time, foot of newt or something probably had some whole resonance of what that meant, which is completely lost, at least for me today. So it would make it very hard to read that, even if one could get through the, what code did they use? I doubt that the actual codes they used, if they were mathematically derived codes, were anything difficult to break in modern times. But codes that are like, I'm going to say newt when I mean chicken, those are sort of off the table because you have no idea what that sort of code word translation might have been. M. Rudo is asking, was Newton not an alchemist? Yes, indeed. Newton, we know Newton mostly for his contributions to mathematical science, but he did a bunch of other things as well. I mean, he was, he was the member of Parliament for Cambridge, although I think he spoke only once in Parliament. He was not content with being a professor in Cambridge. Later in his life, actually through his niece, Catherine Barton, he ended up with this job of being controller of the mint, basically Treasury Secretary in England. And he was, for example, one of his ideas, I think, was to make one of his ideas was to put serrated edges on coins so that people couldn't, when sort of the value of the coinage went out of whack with what it was actually worth, people were kind of scraping pieces off, or actually even when that wasn't happening, they were scraping pieces off the copper pennies and turning them back into lumps of copper, and putting these serrated edges made that harder to do. I think he also was responsible for the idea that British money would have weights where the different coins would have weights that weren't rational multiples of each other. So that if you took just a whole pile of assorted coins and just weighed them all together, you could decode how many of each kind of coin you actually had. I must say, I was once disappointed when I was a kid and I had all this cash and I had carefully sorted it into all these different, the pennies and the shillings and all this kind of thing. I take it to a bank and they just break open all of my, carefully sorted envelopes or whatever they were, just put them all into a machine, and which was a weighing machine. I mean, in modern times, there are sorting machines that sort by size, but I think in those days, it was just a straight weighing mechanism, following the Newtonian tradition, so to speak. But yes, Newton did a bunch of other things. I mean, Newton also had a whole religious theory. I think he was a Trinitarian or something, and he had a whole theory about, I don't know it at all, but he had a somewhat unusual kind of theory about the Holy Ghost and other things. That was a whole other branch of his thinking, and he also did alchemy. I mean, he did experiments. One of the things that he was, I think, was not always the case. There were people who were really natural philosophers who just sat around and thought about how nature worked. Newton actually did experiments, including some sort of psychophysical experiments on himself, that He was using prisms and he was looking at actual things that in the world. And one of the things he looked at a bunch was chemistry and what was then called alchemy. I mean, it's the last book he wrote in his life, it wasn't published until after he died, was a book called The Chronology of Ancient Kingdoms. And it was a book that attempted to sort of outline all of history to figure out just when did, the Exodus happen or something like this. So just when did some event described in the Bible happen? And he was interested in that because he was trying to use that as a sort of anchor for observations in astronomy. But it's sort of an interesting book where he tried to kind of tried his hand at history, so to speak. So Des comments, the real secret is it's tungsten that can be turned into gold, hence the name Wolfram Research. Yeah, well, the amount of email that I get of people trying to sell me tungsten-related products is surprising. Wolfram being the European, the European name for tungsten. All right, let's see, maybe one more question and then I should wrap for today. Social asks, Dirac, Einstein, Turing, and Feynman are sitting in a room. What is the single word they all immediately agree on? Well, let's see. Of those four people, the only one I knew was Dick Feynman. I've heard lots about the others from many people. One interesting question is, did those four ever meet? So Dirac and Feynman definitely met because Feynman told me a bunch about Dirac. He said about Dirac, it was hard to ever get more than one word out of Dirac. That Dirac was a very formal kind of person who would answer most things monosyllabically. He was, I think in his later years, he had been in Cambridge for a long time and they had a sort of mandatory retirement age. In his last few years, he went to Florida and people say that he really opened up when he went there, but I don't know if that's the case. But anyway, so Dirac said few words. Dirac was quite monosyllabic, so he would be a challenge to get to say very much at all in this setting. So Dirac and Einstein certainly met. Einstein and Feynman certainly met at Princeton, but I don't remember Dick Feynman ever talking about Einstein, now that I think about it. I think Einstein, by the time, Feynman was a graduate student in Princeton in the 1940s. I think by that time, Einstein was viewed by most people as kind of a kindly old chap who worked on his unified field theory and nobody really believed it was going to go anywhere. So probably perhaps they just were not so interested in interacting. I mean, Feynman's advisor, John Wheeler, certainly had interacted with Feynman, but I don't know whether he was actively doing so at that time. Alan Turing, did he meet these other people? So Alan Turing was mostly in England. He was very briefly a graduate student in Cambridge working with Alonzo Church. That was in 1937, 1938 kind of time frame. Let's see. Well, let's see. Turing was in Cambridge certainly at the same time as Dirac. Ah, yes, here's an interesting factoid. I don't know if they ever met, but I actually have a copy of Dirac's book on quantum mechanics that was at one time owned by Alan Turing. So I was given that book by a former high school teacher of mine who got it from another former high school teacher of mine who had been a friend of Alan Turing's and who, when Alan Turing died, there was sort of a who wants to take his books? And this person named Norman Routledge took various books, including this book of Dirac's quantum mechanics, actually the German edition of Dirac's quantum mechanics, that, as I say, had been owned by Alan Turing, and I now have that book. Now, whether Alan Turing met Paul Dirac, he must have done, because Cambridge was just not that big a place. now that I think about it, he was Alan Turing was interested in physics, got interested in physics um, in around 1935, 1934 type timescale. And there was a physicist in Cambridge who had sort of encouraged him to study various things about quantum mechanics. And so I would have to believe he met Dirac, but I don't know of any notable interaction between them. I think each of these people have very different. Dirac was a very sort of formal, precise, kind of very mathematically oriented, although not, he sort of invented some of his own mathematics, but he wasn't sort of I'm about to do algebraic topology. He was more of a sort of 19th century math plus his own additions type thing, but very much of a sort of a formalist at that level. I don't think Dirac was, I mean, he invented the Dirac equation in maybe 1930, late 1920s, early 1930s. It's the equation for relativistic electrons. And one of the things about it is it has solutions that correspond to negative energy levels. And Dirac kind of interpreted that as an antiparticle of the electron, predicted the existence of the positron, but nobody really took that seriously until a chap called Carl Anderson actually found a positron in cosmic rays. And then people took it very seriously. But Dirac was very much of a formalist. Alan Turing was, I would say, much more of a conceptual thinker in many ways, and a formalist by necessity rather than a formalist by avocation, so to speak. And I think, Alan Turing was, his proofs, his papers were sort of full of bugs. The ideas were very strong. The details were a little bit sort of all over the place. I think so. It's hard to think. Oh, so Einstein was kind of again sort of wheeled in the mathematics he needed, but was not as much of a formalist as Dirac. I mean, Einstein sort of had a much more philosophical point of view. I think Einstein and Turing, in many ways, had quite a lot in common in terms of the way that they thought about things, although the subject matter they thought about was very different. Dick Feynman, well, gosh, at some level, he was very much of a calculator, but what he prided himself the most on was kind of intuitive explanations of things. I'm not sure, with Dirac, as I say, Dick Feynman told me about his conversations with Dirac, and he said they were very difficult, and that, they would go on a walk, and Feynman would be going yakety, yakety, yak, and Dirac would say nothing, and eventually one word would come out. He said it was better than going on walks with Niels Bohr, because with Niels Bohr would be talking continuously, but Feynman couldn't understand a word he said because the English was so accented in Danish and perhaps not even very good English that he just couldn't follow anything. But in any case, I think, by the way, I think Dick Feynman and Alan Turing will never have met. I think I could say that with considerable certainty. There's just not a place where they would have intersected. And I think Dick Feynman was interested in computers. He had been in the Manhattan Project, for example. He was the head of the human computers. In those days, there weren't electronic computers. There were maybe some electromechanical ones, but there weren't modern electronic computers. It was too early for that. But there was a group of mostly women who were the human calculators, so to speak, who would do by hand these kinds of calculations. And Feynman was in charge of that. And Feynman was always very interested in sort of things about computers. I doubt that he knew what a Turing machine was. In fact, I wouldn't be surprised if I was the one who told him what Turing machines were. I'm not certain of that, but I wouldn't be surprised. Turing machines were not sort of a common, they were a thing studied in theoretical computer science. They weren't really a thing which would intersect with something like physics. Yes, so I don't know what that crowd would um, would necessarily agree on. I mean, they might all think that, well, I guess they all, in some way, yeah, I mean, they all were users of mathematics, although in somewhat different ways and with somewhat different attitudes towards mathematics. They were, I would say, with the possible exception of Dirac, well, Feynman was not a, Feynman would say of himself that he was not a philosophical thinker. He was always horrified. He always said philosophy is all nonsense. They have nothing interesting to say. And so when his son Carl majored in philosophy at MIT, that was kind of a, Carl did that, I think, as kind of a comment on the idea that sort of philosophy is not really a thing. But in any case, so Feynman at least would give lip service to the idea that philosophy wasn't really a thing. I think Einstein would have been much more kind of philosophy is a thing, and he could discuss things philosophically and talked about, you know, the ideas of Ernst Mach and people like that. Turing, in his later years, certainly was interested and aware of philosophy. He'd gone to lectures by Ludwig Wittgenstein, and you know, when he started sort of talking about kind of how thinking works and the Turing test and, you know, early ideas of AI and so on, that was quite philosophical. My guess is that Dirac, again, would have eschewed all philosophy. Dirac was just like, give me the math, give me it precisely, so to speak. I mean, I know Dirac, actually, Norman Routledge, who, as I say, was a friend of Alan Turing's and a high school teacher of mine. Norman Routledge knew Dirac's son quite well, and said he'd been at, you know, visited the Dirac house many times, and that Paul Dirac, the original famous Dirac, was very big on sort of mathematical toys and so on, but was very kind of you know, always into these kind of what today we might call sort of geek hacky type things. And I guess Dick Feynman also kind of liked those kinds of things. I don't know. Okay, so yes, there's another commonality here. I think Alan Turing was also something of a hacker at that level, and something of an enthusiast of these kinds of cool kind of conceptual toys. I don't think Einstein was into those kinds of things. So I'm having a hard time here making something which is a full intersection of all those four characters. But I suppose at some level they were all interested in physics, although Alan Turing never got very far in thinking about physics. He kind of wanted to learn about it, but never really did. But the others, Feynman was sort of interested in computers, but didn't really learn theoretical computer science until much, much, much later. Einstein and Dirac, I doubt they had any awareness of computers. Well, maybe Einstein in his later years, because he was at the Institute for Advanced Study, where John von Neumann was, and John von Neumann was building this computer that got called the Johnniac, which was he built in a building at the Institute for Advanced Study. An interesting question is whether Einstein ever went into that building. I do know that Einstein took walks around the Institute grounds, and there's a famous picture of him with Kurt Gödel taking a walk. And I'm pretty sure that the walk they were on in that picture is a path that actually I used to walk regularly, that went right past what was, when I was at the Institute for Advanced Study in the early 1980s, was still called the Electronic Computing Building, although by that time I think it was a preschool. So I think if Einstein didn't see that computer, at least he walked past it a bunch of times. Anyway, so Harry is commenting. So Dirac answered in Dirac delta function style. The Dirac delta function is this sort of limiting mathematical function that's zero everywhere except at x equals 0, where it's infinity. Yes, I suppose that's right. I mean, Dirac was a very clean formalist. I mean, he invented formalism that was very like the Dirac delta function, like Bras and Ketz and so on, that was very, very clean. I would say that the others, Einstein also was a sort of a clean inventor of formalism. Turing, not so clean. Formalism that was clean in its ideas, but if you look at the original paper on Turing machines, it's festooned in Gothic letters and a very Baroque, actual notation. What Turing talked about, Greek letters and German letters, which we would now call Gothic letters. All right, I'm being reminded that I'm late for something in my day job here, so I think I better wrap up here. But thanks for lots of interesting questions. I see many more that I would have loved to get to this time, and I'll have to get to them another time. But thanks, and bye for now.